I hope you had a good one. I know I enjoyed my time away from distance learning. It's a good time to refresh and kind of refocus on, you know, things are kind of normal. It was kind of nice. I hope you guys had a similar experience. All right, so we're going to kind of wrap up solving systems before we enter into second semester. We already finished the graphing portion of that. You're still welcome to retake that assessment if you would like to, or finish it for that matter. But we're going to go ahead and move on to the algebraic techniques to solve systems of equations. So today we're going to start with talking about substitution. Before I jump into the notes themselves, I just want you guys to kind of think about what the word substitution means in itself. When I think about substitution, I usually will think about sporting events. So, for example, if we're talking about basketball, if a coach will substitutes out a point guard, they will usually put back in the equivalent, which would be another point guard or somebody who can play that position. In football, if you take a quarterback out of the game, you're usually going to put a quarterback back into the game, so you're going to substitute it with an equivalent. If you're talking about soccer, if you pull a goalie out, you're going to put a new goalie back in the game, kind of that idea. So substitution generally means you're going to take something out and replace it with an equivalent. Now in math, we are literally mean equivalent. So something that is mathematically the same. Now remember, that might not mean it appears the same, but mathematically speaking, it will be the same. And that really goes down to what that equal sign means. The equal sign means equivalent, right? If 2x equals 4, we know that 2x is the same as 4, which means they are interchangeable pieces. So just keep that in mind. Either side of the equal sign is equivalent. All right, so today what I want you guys to do is I want you to get the notes portion down. So the procedure 1 through 4 down here. And then I would like you to also go ahead and take notes on the first example. At that point, you can pause and we will do the rest in class together. That will include going over that first example again and then doing the 2 remaining examples on the notes. I'm hoping when you come to class you will have questions both on the notes themselves and on the one example, and it'll kind of prime you for getting ready to learn this material. All right, so let's jump right in. Step 1 is to solve one of the linear equations for a variable, isolate x or y if necessary. So that basically means we want to either get the x or the y by itself for one of the 2 equations. It doesn't matter which one, and it doesn't matter which variable. So we want to end with something like this. Let's say one option would be have something in slope-intercept form. So y equals 2x plus 6 would be an example of the y being isolated, right? So that's an example of where the y is isolated. Okay, step 2 is we're going to place the variable in the second equation with the expression that you solve for in step 1. Solve for the variable in your new equation. So basically that means we're going to take the expression that equals the isolated variable. So in this case, we're going to take 2x plus 6. And in the other equation, the equation you haven't seen here in the procedure, we're going to replace the y variable with the expression 2x plus 6. This is confusing. I do not expect you guys to completely understand that for a couple attempts at this at least. Hopefully the first example will help clarify what that actually means. All right, step 3 is you're going to substitute your solution into the equation from step 1 to find the value of the other variable. State your full answer as an ordered pair. So remember, when you're talking about a system of equations, the answer is the x and y coordinate that will satisfy both equations, right? So basically where those 2 lines cross. Finally, this step is actually the same as graphing. You're going to verify the ordered pair is a solution by substituting x and y values into the equation in the system or by graphing the system to confirm that the point of intersection matches your solution. I'm going to highly recommend you don't graph. Plug the numbers back in and make sure it gives you a logical statement and then go from there. All right, so let's go ahead and look at the first example. So the first example, step 1 is already done. But before we jump into that, I want you to recognize when I do these, I will often model them using kind of like a quadrant system. So for substitution, I will start by doing step 1 here, right? Sometimes step 1 is done. In this case it is. And I will do step 2 here. I'll do step 3 over here. And I'll do step 4 over here. So this is, I'm going to isolate a variable right here. When I get to this part, I'm going to solve for my first variable, then I'm going to solve for my second variable, and then give the answer, and then I'm going to check to make sure it all works. Okay, so for our first example, we actually have an isolated variable already. So in our first equation, it's in slope-intercept form. We have y equals negative 2x plus 5. So in this case, we have This expression right here, negative 2x plus 5, is equivalent or equal to y. That means y is the same thing as negative 2x plus 5. Now we can use that powerful tool to put this expression in the second equation in place of y. Right? So since y is the same as negative 2x plus 5, I can replace y with negative 2x plus 5. So that means we can already move down the second part where we're going to solve for the first variable. So I'm going to take this equation, I'm going to write it out as 4x plus 3. Now instead of putting y in there, I'm going to replace that y with negative 2x plus 5. And that still equals 9. So if you look at this, I'm going to highlight what happened. This and this, same thing, right? I just replaced y with an equivalent. Now we are solving an equation like we normally would. All right, so now we're back to what you guys learned last year and we reviewed this year. We're just going to distribute. So I have 4x minus 6x plus 15 equals 9. And I'm going to go ahead and combine like terms. 4 minus 6 is negative 2x. All right. Now I'm going to subtract that 15 away from the variable. I'm left with negative 2x equals negative 6. Then I divide by negative 2. And I get x equals 3. Okay. So I have solved for my first variable. I think the x-coordinate for my intersection point is 3. Okay, great. Halfway there. I'm going to pick either one of these equations. Doesn't matter. I'm going to go ahead and use the top one now. So I'm going to plug in and take that. I'm going to get y equals, and now I'm going to replace that x with 3. All right. So I replace the x right here, this x, with the value 3. I'm just going to solve for y. Y equals negative 2 times 3 is negative 6 plus 5. Negative 6 plus 5 is negative 1. Okay, now I have my x and my y, so now I can go ahead and write down what I think my ordered pair is. 3, negative 1. Okay, ordered pair right there. Okay, now I'm going to go down to the next cell, and I'm going to check to make sure it works. So I'm going to take this ordered pair, and I'm going to plug it back into both of my original equations, which in this case we didn't convert anything, so easy, to verify that it gives me a logical statement. So y, for y I'm going to put in negative 1 equals negative 2, and I'm going to put in 3 for the x plus 5. If this works, then it works for the top equation. Okay, negative 1 equals negative 6 plus 5. Negative 6 plus 5 is negative 1. Negative 1 equals negative 1. That indeed works. Okay, let's do it for the second equation. So we have 4. Okay, we have 4x, and we're going to replace x with 3, plus 3, and then we're going to replace the y with negative 1, equals 9. Okay, so 4 times 3 is 12. 3 times negative 1 is negative 3. 12 minus 3, 9 equals 9. It works. Therefore, that is our correct answer. Okay, that's the first example. This one was convenient because we didn't have to convert anything. We just had to plug stuff in. So recognize we had the y was isolated already, so we took the equivalent expression and we plugged it in for the y in the second equation. We can do that because they are equivalent. Then we solve for x. After that, we took the value of x and we plugged it back into the top equation for x. So we plugged 3 in for x, and then we solve for y, which is negative 1. And then finally, we check to make sure it's correct. All right. I would like you to pause the video now. You're done taking notes. We're going to do the rest in class. If you miss class, you can continue watching for the next 2 examples. All right. Okay, next example. This time, instead of having the y isolated, we have the x isolated. So we have this expression 4y minus 5 is the same as x. So I'm going to plug that in for x in the second equation. All right, so my new equation after I rewrite it will be 2. Once again, replacing the x with 4y minus 5. We can do that because they are equivalent. And then we're going to add plus 3y equals 23. All right, now we are just solving for the y variable. Okay, so distribute 4y minus 10 plus 3y equals 23. Combine like terms, 8 plus 3 is 11y. Okay, now I want to move the constant, so I'm going to add 10 to both sides. 11y equals 33. Divide everything by 11, y equals 3. Okay, now we think y equals 3, so what I'm going to do is the same thing I did before. Last problem, I'm going to plug y equals 3, or the value 3, into the equation for y. So x equals 4, replacing that y with 3, minus 5. Now I just go ahead and simplify the right side. 4 times 3 is 12. 12 minus 5 is 7. X equals 7. Therefore, we think, keyword there, think, our solution is 7, 3. So 7, 3. Now we're going to check that to verify it works. All right, so x equals 4y minus 5. So we're going to plug in 7 equals question mark 4 times 3 minus 5. Okay, 4 times 3 is 12. 12 minus 5 is 7. 7 equals 7. It works for the first one. Now we're going to do the same thing for the second equation to verify it works as well. 2, my bad pen stroke there. 2 times 7 plus 3 times 3 should equal 23. Okay, 2 times 7 is 14. 3 times 3 is 9. 14 plus 9 is 23. 23 equals 23. That works. That works as well. All right, so far so good. So this equation, instead of the y being isolated, it was the x. But the same basic procedure. All right, last example. You'll notice this one, we do not have a single variable isolated. The x and y are on the same side. The x and y are on the same side. Now, in this scenario, remember, you only have to convert one of them. So I would recommend you convert the one that takes the least amount of work. So what I will look for is a naked variable, a variable that's all by itself. In this case, I have an x that has no coefficient, and I also have a y that has no coefficient. So I'm going to convert the second equation. So I'm going to go rewrite it over here so I have a little room to work. X plus y equals 5. Now I'm going to go ahead and just isolate the y variable. So I'm going to subtract x on both sides. Remember, if you do the same thing to both sides of the equation, it is the same equation. So you get y equals 5 minus x. Now I have my y isolated, and I have this expression x minus 5. Now I can put this x minus 5 into my top equation for y. All right, and then I can go ahead and solve. So I have 4x minus 3, then I'm replacing the y with the equivalent expression, which is 5 minus x. And then setting that to equal to 15, negative 15, sorry. And I'm just going to solve just like I have been doing, so distribute. So I have 4x minus 15 plus 3x plus 3x equals negative 15. Okay, combine like terms, 4 plus 3 is 7x. Add 15 to both sides. Okay, so I have, this goes away. 7x equals negative 15 plus 15 is 0. Divide everything by 7. X equals 0. That's convenient. 0 is really easy to work with. Okay, x equals 0. Yes, it can happen. Either one of the variables can equal 0. So if you see that, might do a quick check to make sure you did your work correctly. Chances are you're right, though. Okay, now I'm plugging that x equals 0, and I'm plugging into the top equation for x. So I have 4 times 0 minus 3 multiplied by y equals negative 15. That cancels out. I have negative 3y equals negative 15. Divide both sides by negative 3. Y equals 5. So we think our ordered pair, our solution is 0, 5. Okay, now just like with graphing, if we had to convert something to slope-intercept form, we don't check our work using our new version of the equation. So we're not going to check our work using y equals 5 minus x. We're going to check it using x plus y equals 5. The reason being, if I made a mistake converting, I could be checking my work for the wrong problem, so make sure you're using the original equation. So let's go ahead and start by checking for 4x minus 3y equals negative 15. So for the x, I'm going to plug in 0. So I have 4 times 0 minus 3 times 5 equals negative 15. This cancels out. Negative 3 times 5 is negative 15. Negative 15 equals negative 15. That's correct. Okay, let's do the same thing for the second equation. I have x, which is 0. 0 plus y, which is 5, should equal 5. 0 plus 5 is 5. 5 equals 5. It works for both, therefore it works overall. Okay, that was a quick intro to the substitution technique. Hope this was helpful. Yeah.